Welcome to my second lecture of computer aided electrical machine design. I have completed 12-week course on computer aided design of electrical machines offered by Indian Institute of Technology, Delhi. This is my NPTEL online certificate. In this lecture, I will discuss about magnetomotive force, its importance in electrical machine design, flux density, what is CRGO core, and stacking factor. So first of all, we have to understand what is the meaning of magnetomotive force. Magnetic circuits are fundamental in devices like transformers, motors, and generators. A magnetic circuit is a closed loop path that allows magnetic flux to flow, similar to how an electric circuit allows electric current to flow. It is the force that drives magnetic flux in a magnetic circuit, analogous to electromotive force in an electrical circuit. MMF is the pressure or driving force that creates and maintains magnetic flux within a magnetic circuit. Unit of the magnetomotive force is in ampere turns. The formula for the magnetomotive force, the MMF, is calculated as the product of the number of turns in a coil and the current I flowing through it. Therefore, we can write MMF is equal to N into I. The magnetomotive force MMF is defined as the work done in moving a unit magnetic pole once around the magnetic circuit. Another formula to calculate the magnetomotive force, let us we consider the diagram. In any magnetic circuit, if H being the magnetizing force and L is the length of the magnetic circuit, then the magnetomotive force for the magnetic circuit is given by MMF is equal to H into L. In any magnetic circuit, if phi being the magnetic flux and S is the magnetic reluctance of the magnetic circuit, then the magnetomotive force required is given by the equation MMF is equal to magnetic flux into reluctance. So we have to put the relation of the magnetic flux reluctance in the equation. So MMF is equal to that phi into L upon A mu 0 mu r. We have to rearrange the equation in the suitable form. Therefore, we can arrange the equation phi by A into L upon mu 0 mu r. As you know that reluctance can be write in the form of L upon mu 0 mu r, and phi by A is equal to B, that is magnetic flux density. Therefore, we can write the equation of magnetomotive force is equal to B into L upon mu 0 mu r is equal to H into L, where H is equal to that B upon mu 0 mu r. One numerical example, an electromagnet having a coil of 1500 turns, if 2 ampere current flows in the coil, determine the magnetomotive force of the electromagnet. So this numerical is so simple. MMF is equal to N into I. Therefore, N is equal to 1500 and current is 2 ampere. Therefore, in the equation MMF is equal to N into I is equal to 1500 into 2. Therefore, 3000 ampere turn required. Let us say consider another example. A magnetic flux density of 1.6 Weber per meter square is required in the air gap of 4 mm. Calculate the MMF required. So, magnetizing force H is equal to B upon mu 0. Put the value of B is equal to 1.6 Weber per meter square in the equation. Mu 0 is equal to 4 pi into 10 raised to minus 7 in the equation. and calculate the H. So H is equal to 1.273 into 10 raised to 6 ampere turn per meter. Therefore, MMF required is equal to H into L. H is equal to 1.273 into 10 raised to 6 multiplied by 4 into 10 raised to minus 3. Therefore, MMF required for this particular example is 5092 ampere turn. The magnetomotive force MMF for an air gap is calculated using the formula MMF is equal to B into L upon mu, where B is the flux density, L is the air gap length, and mu is the permeability of the air gap. Essentially, it is the driving force that creates the magnetic field across the air gap. Let us say we consider one example. Let us say we have the flux density B is 0.88 Tesla, the air gap length L is 8 mm, and the permeability of the air mu is, let us say, given 4 pi into 10 raised to minus 7 Henry per meter. So using the formula of MMF is equal to B, we consider here B is equal to 0.88 Tesla. Length is given here 8 mm. So therefore we have to convert this length into the suitable unit. So we have 0.008 meter divided by the permeability of the air is 4 pi into 10 raised to minus 7 Henry per meter. Therefore, MMF is equal to 5600 ampere turn. This question was asked in the one of the competitive exam of DFCCIL Junior Engineering Exam 2021. Let us say we consider another example, and the data is the magnetic circuit shown below has uniform cross sectional area and air gap of 0.2 cm. The mean path length of the core is 40 cm. Assume that leakage and fringing fluxes are negligible. When the core relative permeability is assumed to be infinite, the magnetic flux density computed in the air gap is 1 Tesla. With the same ampere turns, if the core relative permeability is assumed to be 1000, let us say linear, the flux density in Tesla round off to 3 decimal places calculated in the air gap is. So we have to find out the B2 for this particular the example. Now if we have the 40 centimeter the path, therefore here we have the square cross sectional area. So we have the 10 centimeter all the sides of the square, and there is a 0.2 centimeter the cut in one of the side of the square. So according to the geometry, we have to use the equation, and for the case number 2, if the permeability of the core is 1000 linear, then we have to use the equation Rm2 is equal to that R1 plus R2, that is the reluctance of the circuit. Using this relation, we can calculate the Rm2 is equal to that 39.8 upon 10 raised to 3 mu 0 A plus 0.2 upon mu 0 into A. Why 39.8? Because we have to subtract this 0.2 centimeter from the total the flux path of this square. So using this relationship, we come to know that Rm2 is equal to 1 upon mu 0 A, and solving these numbers is equal to that 0.2398. Now using the equation of relation between the B1 and B2, the B1 upon B2 is equal to that Rm2 upon Rm1. So putting the value in the equation, finally we will get the B2 is equal to 0.83. Magnetizing current, because when you consider the transformer design or any electromagnet or any electrical machines, we have to also that calculate the magnetizing current. What amount of the current is required? So to calculate the magnetizing current in a magnetic circuit, you need to understand the relationship between magnetomotive force, flux and the reluctance. So the MMF is created by the current flowing through the coil. You know that formula, N into Y, where N is the number of turns and L is the current. The flux is related to the MMF and the reluctance S by the equation. You know that flux phi is equal to that MMF upon reluctance. This equation is somewhat similar to that current is equal to that EMF upon resistance. Reluctance S in turn depends on the length, area and the permeability of the magnetic material. Let us say consider the another example. You have a coil with 1000 turns and you want to create a flux of 1 Weber in a magnetic circuit. The magnetic circuit has a path length of 1 meter, a cross-sectional area of 0.01 meter square and a permeability of 10,000. So calculate the magnetomotive force using the equation is equal to that N into Y. Calculate the reluctance using the formula S is equal to that L upon mu 0 mu R into A. And therefore we have the S means reluctance in our case 100 ampere turns per Weber. Calculate the current using the equation flux phi is equal to that MMF upon S. Therefore we have 100 ampere turns and according to that the requirement, putting the value in the equation, we will get current I is equal to that 0.1 ampere. That is the magnetizing current. It means when you pass the 0.1 ampere current through the magnetic circuit, you will create the certain the requirement, because we have to create the flux in our circuit is about 1 Weber in the magnetic circuit. Now very important term is the flux density in the electrical machine design point of view. So we have to understand what is the importance of the flux density, because when you are going to design the transformer, we have to assume the flux density for distribution transformer, for power transformer, according to that our requirement. So again, in the final year, we have to understand about the flux density. So what is the meaning of the flux density? So in a magnetic circuit, real flux density represents the actual flux passing through a specific area, while apparent flux density represents the total flux passing through an area, including flux that might not be used to the main part. All the students please understand the real flux density and the apparent flux density. So the apparent flux density may include flux that is not confined to the main magnetic path, such as the leakage flux, joints in the magnetic circuit. Apparent flux density is always greater than or equal to the real flux density if you minimize the joints. So look at the figure and understand how much flux is passing to the unit cross sectional area. That B is equal to phi by A, Weber per meter square. This is the unit of the flux. Current carrying conductor and magnetic field. We have learned about the existence of a magnetic field due to a current carrying conductor. We have also learned that an external magnetic field produces a force on a current carrying conductor. Thus, from the two studies, we can say that any two current carrying conductors, when placed near each other, will exert a magnetic force on each other. So let us say we consider the system shown in the figure below. Here we have two parallel current carrying conductors separated by a distance d such that one of the conductor is carrying a current I1 and other is carrying I2 as shown in the figure. From the knowledge gained before, we can say that the conductor 2 experiences the same magnetic field at every point along its length due to the conductor 1. The direction of the magnetic force is indicated in the figure and is found using the right hand thumb rule. The direction of the magnetic field, as we can see, is downwards due to the first conductor. This principle you have studied in the first year basic electrical engineering. From the Ampere's circuital law, the magnitude of the field due to the first conductor can be given by B is equal to mu 0 I upon 2 pi r. The force on a segment of length L of the conductor 2 due to the conductor 1 can be given as F21 is equal to mu 0 I1 I2 upon 2 pi r. Similarly, we can calculate the force exerted by the conductor 2 on the conductor 1. We see that the conductor 1 experiences the same force due to the conductor 2, but the direction is opposite. Thus, we can write the relation of F1 to 2 is equal to that minus F2 to 1. We also observed that the currents flowing in the same direction make the conductors attract each other, and that showing in the opposite direction makes the conductors repel each other. Now, why we study this theory, and here we understand from this transformer point of view which winding of the transformer would be closest to the core, and the question is the why. So first of all, we have to understand the cross-section view of the transformer, the position of the windings and other parts of the transformer. So which winding of the transformer would be closest to the core and why? So for this particular transformer, for a 2 winding per core leg transformer, the low voltage winding is placed closer to the core than the high voltage winding. The core iron is constructed so that it can be single point grounded to the tank. By placing the lower voltage winding closer to the ground core, then the higher voltage winding less insulation is required, number 1. In addition, the high voltage winding requires a greater number of turns, and sometimes tappings also possible for voltage regulation. Placing the high voltage on the outside becomes the practical choice regarding this. Another major factor has to do with the forces acting on each winding during a short circuit event. The magnitude of the vector forces acting on each turn of a winding is approximately proportional to the current magnitude squared that we have seen in the last slide. Since the low voltage winding has few turns, the magnitude of the current is much greater than it is in the high voltage winding, and therefore the short circuit forces are also greater. When the low voltage winding is placed on the inside, its dimensions can be made smaller, and this translates to a mechanically stronger winding requiring less bracing material than what would be required if it were placed on the outside. So in the figure you can see that the position of the low voltage winding and the high voltage winding. You can also see the bracing in the figure, and also we can see the step changer in the transformer. Another question is that types of the material, and generally we always speak in terms of CRGO core. So we have to understand what is CRGO core. Sit steel which has been rolled such as to give easy direction to all its crystals is called textured or grain oriented steel. Figure 1 shows sit steel with unfavorably oriented, or we can say that non-oriented grains. Figure 2 shows sit steel, the grains of which are oriented in the direction of the rolling. This is the manufacturing process. It is easier to magnetize the grain oriented strip shown in the figure 2 in the rolling direction than the randomly oriented, or we can say that non-oriented strip shown in the figure 1. Non-oriented sheets require a higher magnetizing field to magnetize them. Figure 3 discuss the great advantages of higher permeability and higher saturation values obtained from non-oriented silicon steel over plain cast iron, and even greater advantage of grain-oriented silicon steel over the non-oriented silicon steel. So this graph is plotted for different materials with the different combinations. And according to that graph, you come to know that which is advantageous. So generally, in the Viva, or you can say that during our discussion of electrical machine and machine design, we always discuss about the CRGO. So summary of this cold roll grain oriented steel. Grain orientation means CRGO steel has its grains crystals aligned in a specific direction, primarily along the rolling direction. This alignment significantly improves its magnetic properties. The aligned grain results in higher magnetic permeability and reduce hysteresis and eddy current loss, reduce energy losses. The combination of high permeability and low losses translates to higher transformer efficiency and less heat generation. Corrosion resistance. CRGO offers increased resistance to corrosion, extending the lifespan of the transformer core. Applications of CRGO material. CRGO is mainly used in the power transformer, distribution transformer, and large rotating machines. Laminations. CRGO steel is typically used in the form of the thin laminations, which are then stacked and assembled to form the core of a transformer. The another very important definition is about the stacking factor. The stacking factor in a transformer core is the ratio of the net cross-sectional area of the core, or you can say that the area occupied by the magnetic material to the gross cross-sectional area of the core, or you can say that the total area of the core including laminations and the insulation. It is always less than 1 because laminations and their insulation take up some space within the core. So when we are going to the design the transformer, again I will discuss the term stacking factor. Thank you very much.